Hello, my name is JQSun1. I'm a professor and chair of the Department of Mechanical Engineering at the University of California, Merced. Today, I'd like to report two recent studies of nonlinear stochastic systems in which we use the concepts and the methods from data science. Now, here's the outline. There are two topics I'm going to talk about today. The first one is the data-driven global analysis. The second one is the improved least mean square method for stationary solutions of FPK equations. Now, we are in the age of data science. There's a lot of studies and interest in big data, deep learning, and artificial intelligence. As mechanical engineers, we ask this question: what can we do given lots of input-output measurements of dynamic systems? Well, there have been many activities in engineering. For example, the fault detection and health diagnostics. That part of the study of engineering has been traditionally based upon data, right? And another part of the study is the system model development and parameter identification, known as the system ID. It's been very commonly practiced in structural community. And then in the control community, there's also a lot of work on building the local model and use the model to do control design. And then, of course, when you talk about control design or system design, there's always an optimization issue. So there are studies based upon the data, try to improve the performance of control systems, like using so-called reinforcement learning. It's been very popular right now. The question we are trying to answer is here: can we actually do global analysis of nonlinear dynamic systems if we observe the response of the system for a long time? So global analysis with data only is really a new idea, a new topic. So we don't need differential equations anymore. We only rely on measured response. And then we have to point out the measurement usually is a linear combination of the state variables. And you don't know what state variables are because you don't have equations, right? And also state variables themselves are not unique. So you only rely on the data. Okay, therefore, depends on how you formulate some state space representation from the data. The manifold of those nonlinear elements like period orbits or the chaotic motions, the geometry may change depending on what kind of variables you're going to use to describe them. And then we also need to know the dimension of the underlying state space. From the data, we don't really know. One interesting observation in this study is that we found a tremendous benefit of the noise, the random noise in the measurements. It actually has a very beneficial effects. So to do global analysis, we used the very well-known method called cell mapping, in particular the generalized cell mapping method. Essentially, the idea is to discretize the state space into little boxes, and then you integrate the differential equations from all possible initial conditions in the box. Then it maps to some domain, and then that creates what is known as the probability mapping from one state or one box to another. Therefore, it's called the cell mapping. And each cell is mapped to multiple cells, so it has multiple images. Automatically, it's very naturally that this description of dynamic systems leads to the Markov chains. Okay, traditionally, We use differential equations to create generalized set mapping. We use Monte Carlo simulation. We use short-time approximate solutions to speed up the calculations. And for the first time, we actually use the measurement data. If you just use measurement data to create the generalized set mapping, it becomes a very well-known statistical problem. It's called density estimation. It's been studied in that community for many, many years. So in order to do data-driven global analysis using set mappings, we need to assume that we have a collection of a larger set of long histories of response measurement with random noise. Remember, the random noise is beneficial to you. Then we need to know what to do. Okay, so we're going to do the global analysis to find out the global properties of the underlying dynamic system just by looking at the data. Before you can do the set mapping, you need to pre-process the data to get two pieces of information out. The first one is the embedding dimension. You need to know the data behind it. What's the dimension of the state space? And then secondly, since you are doing mapping, then you need to know what mapping step, the time step you may need. Okay, it turns out the embedding dimension is a very well-known topic studied for many years back to the 80s, 70s, and by 90s, it became very mature discipline. So there are several methods out there you can study or you can find the embedding dimension from the measurements. And we are using two criteria to study that. So one is called E1, the other is called E2. Well, I'm not going to give you too much details. You can look up the references, but the fact is that you can find the embedding dimension from the measurement data. And for the mapping step, we use the Fourier transform of the data and trying to discover whether the data is truly random or is periodic, or it is periodic with some dominant frequency and so forth. We use that frequency domain information to decide if there is a proper mapping step we can use. Okay, again, those are the details we can, you can read my paper to find out how to do it. So these are the two embedding dimension definitions, and it's again, it's very well known in the literature. You can find that we just use it. Now, let me just comment a little bit the benefits of noise. Since we are doing the so-called density estimation from the data, we are using the data to estimate the transition probability from one small area in the state space to its images somewhere. So it's really just one step transition probability function. And theoretically, it looks something like this if you use the histogram approach. It turns out in the theory, there's one quantity that actually will influence the way the density looks like. It actually is this Jacobian thing. Okay, the Jacobian more or less indicates the flatness of this function relationship, right? And also the curvature, which we found out back in the 80s, that in order to decide the box size, appropriate box size for partition the state space and using the data, it turns out that the curvature behavior, the curvature of the probability density function actually influences the size of the cells you would need. Essentially, or the message is very simple. It simply says that when the density is kind of flat with smaller curvature, then you can use relatively large cells for a given number of points, data points you have. So that is actually a computationally advantageous to have. Otherwise, imagine that you happen to have almost a delta function density to estimate. Then in order to resolve the probability distribution accurately, you almost need an infinitesimally small cell to do it. So it's not very desirable computationally. Okay, that's really a very interesting observation of the benefits in terms of the density estimation. So here is some definitions of the generalized mapping, like probability vector in the state space, and also the one-step transition probability. So once you define those vectors, then assuming the process is stationary, then the transition probability matrix, this guy is going to be, this will be a constant matrix. And then the dynamic evolution is just simple iteration of the probability vector defined in certain state space. And also a lot of the interesting properties of a nonlinear dynamic system is embedded in the topological structure of the transition probability matrix P. So you can actually partition the P matrix in this form. This diagonal element of the P represents stable solution of the system, and the detailed structure of each P would actually describe the nature of the solution, whether it's a fixed point or periodic orbit, or is chaotic motion. It's all described by that set of P's on the diagonal of the transition probability matrix. And then the last element Q also contains a lot of information about unstable elements of the nonlinear dynamic system, such as saddle points, such as the boundary of the attraction. It's all embedded in that. Okay, there's a lot of details on the generalized mapping that you can refer to the works by my group and my advisors work. So these are the properties of the generalized mapping. So I'm going to just skip this and apply this method to a very interesting engineering example. It's a rotor static rubbing system. When the rotor is spinning and the rotor is supported by a flexible shaft, and shaft will bend. And at some point, the rotor will touch the supporting boundary, and then the equation of motion with probably first model approximation of the shaft is a fourth order or four-dimensional state space nonlinear differential equation. So these are the equations. So in this example, we simulate the data. We have a random noise insert into the equations of motion. We have harmonic excitations. So we collect a lot of data from the system. Now we do FFT. We found out the resonant frequencies of the system. This system has 2 degrees of freedom for the linear states. So you see 2 clear peaks there. So you can actually use those numbers to specify a fundamental frequency of the system. And that may serve as a mapping step for you. And then we also evaluate the embedding dimension index E1 and E2. It turns out about 4, both indices converge to nearly 1. So that's a strong indication that the data we have actually is generated by a 4-dimensional state space system. Okay, then we take the data, we apply it going through the generalized mapping, and we found essentially 2 persistent groups. One is the one that's near the origin, and the other is an orbit, is a periodic motion that's away from it. So you can sort of see this thing, because 4-dimensional space, you have to project down to a 3-dimensional space to see it. So these are the two three-dimensional state space projections. So again, and this is what you can do. You can also, those are the high probability events. Okay, so you see the manifolds of a stable periodic motion, and the red one actually is unstable motion. So now you can also evaluate the probability distribution in the 3D space. And this is the probability density function actually in two-dimensional. You take any two state variable and you plot it out. So you have this kind of very distinct periodic motion distribution, but it has like van der Waals behavior also in the system. Now we now change the subject and then consider a very high dimensional Hamiltonian system. So for example, let's consider this one. This can be n-dimensional Idle equation for the Hamiltonian system. Then we look at the probability density functions of the system, which satisfy the FPK equation. The reduced FPK equation is for the stationary probability density function, which we call the rho here, is the density function. So the partial rho, partial t goes to 0. So we are looking at the stationary solution of FPK. Now, there is a very well-known principle of detailed balance in this stochastic system theory. That this reduced equation can be split into two parts. Okay, then you essentially try to simplify the solution process. So if you can find solutions for these two sub PDEs, which adds up to be the whole PDE, and one part represents so-called circular flow of the probability flow, the other represents the so-called potential flow. So the circular one adds up to be 0, then the potential part adds up to 0. So it needs to these two sets of sub-differential equations. So you can integrate one of them, and then you end up having two separate first order partial differential equations. If these two equations lead to the same solution, now we say the detailed balance condition is satisfied, and then you can actually find the exact solution of this reduced FPK equation. But in general, you cannot find them. If you don't have a closed form solution that exists, it's just then there's no way you can find them. However, these two sets of equations does provide some sort of a solution, like we call this as a phi and psi. And those two solutions, although they don't satisfy the whole FPK equation, but they do carry very important dynamic properties or dynamic information of the original nonlinear dynamic system. So then we propose the approximate solution approach by defining the probability potential function phi here. And phi is defined as a linear combination of these two sets of functions, the phi I and the psi I, and add all those up. Again, the repeated index implies summation. And since these are not necessary to choose solution of the system, then we add polynomials to do corrections to the total solution. So essentially, we say we take the detailed balance suggested approximate function form, or the function form for the approximate solution. And then we use a polynomial, a very generic or general polynomial to do corrections. So this together gives us this total probability potential function. Then we plug this into the equations of motion. And before we do that, we impose some conditions, because you are introducing arbitrary polynomials here. So system may go unstable, right? So the first condition we impose is that the stability of the system must be maintained, which means that in the infinite far away position, when Q, the generalized coordinates, or P, the generalized momentum, goes to infinity, there must be no probability there. So the exponential function of the probability potential must add up to be 0. Okay, so that's a stability condition. Then there is another integrability condition at origin. So you may have the situation that the system may be non-singular, at origin. So we want the whole probability function to be integrable at origin. So this is actually very important, particularly when the system has parametrically excited nonlinear terms. That you may have the singularity at origin that makes the probability density function fail to exist. So now we derive an error function after you substitute the approximate solutions into the reduced SPK. So we end up having this function delta multiply the whole p equal to 0. That will be the condition, right? But since it's not necessarily 0, so we define the error function just by this factor that multiply the whole p, the rho, actually, the probability density function. So then this error is in general a function of the state variables Q and P, and also a function of those undetermined parameters A, B, C. So let me go back to here. So A is the coefficient of psi, and B is the function of psi, the coefficient of psi function, and C's are the coefficients of the polynomials. Depends on how many indices that C has, then represents corresponding certain order of polynomial. So essentially, there are many parameters in C. So we like to essentially make this guy as small as possible in some sense. So the best way to do it is the mean square error. So we like to minimize this mean square error over some domain. This is our proposed method. So once we integrate the error over the state space domain Q, sigma, then the state variables Q and P would disappear. So this J would be a function of ABC, the coefficients only. So from here, you can set a minimization problem, and it come up with a set of non-linear algebra equations to determine ABCs. So that essentially is the whole solution process. Now, as compared to the very classical traditional Galecki weighted residual method, and usually it works this way. You take the error term, you multiply the error term by some base function, and then you integrate that in the whole domain. This is usually done in the textbook. Usually it's integrated in the whole domain, and you set it to 0. Essentially, this implies that you project the error into some functional space, and along all the base directions, the projection must be 0. So that's the spirit of Galecki method. So you have to choose the appropriate function so that this guy is integrable. And most of the time you use some sort of Gaussian distribution functions to do this, because the domain can go to infinite. So in the proposed method, we have to answer the question, what sigma we're going to use. Are we going to integrate the whole 2n space domain or not? So it turns out that from the data science point of view, you don't really need that much. You don't have to, okay? So these are some discussions about how to choose, or the implications of the choice of the computational domain sigma. Okay, and this turns out to be the main trick and also the advantage of the proposed method. So let me just point out here. Suppose you have 2n unknown parameters. This is just arbitrary a number. then you need two independent equations, right, in order to determine those two unknowns. Assuming that you end up having two independent, no, you do have to have two independent equations. And then if the solution is exact solution, then you can actually sample two arbitrary points in the phase plane or in the state space and set the errors to be 0. Then if the equations are independent, then that's enough. You don't have to do integration. However, since you are using the approximate solution to represent the two solutions, so the error may never be 0, right? Therefore, you really cannot just sample a few points and force it to be 0 because the function may never be 0. So you may not even have a solution if you do that. Okay. Another point is that in any finite domain sigma, there are infinite number of points. In other words, if you just integrate in a small domain, theoretically it's enough. And then where the domain needs to be, we found out that if you choose a small domain, that the solution has very high probability there, and then the solution will be very accurate. And the whole process will be very efficient too. So what we end up doing is that we just use -1 to 1 hypercubic domain. It's always integration from -1 to 1. It turns out to be more than sufficient for most of the problem we tested. So this choice of domain really makes the whole method extremely efficient. So let me just show you an example here. This is like a 3-dimensional or 4-dimensional problem. Okay, so you have 4 state variables here. So it has a potential function, and we can, using the detailed balance principle, we can find the phi. There's only one phi we found. We found there's actually 3 psi functions. If you go back to the detailed balance. By the way, those functions are only approximate solutions to the FBK solutions, because the detailed balance may not be satisfied by this system. So that this functions, actually the shapes, the form of the functions are very important because they tend to represent the original system dynamics very well. Okay, then we add some polynomials to this. So this is what we have up to 4th order polynomial. And then you plug that into that process. It takes less than 500 seconds to obtain the whole solution, extremely fast, okay? And this solution is extremely accurate. I'm going to show you the numerical examples later. In the hyperspace probability density function distribution, if you calculate the error, the root mean square error, is in both cases we present is like 10 to the -3. So it's reasonably small. Remember, this is a very high dimensional space, 4-dimensional. It's not easy to compute that accurate solutions. Now again, we actually only use a laptop to do the computation because it's really efficient. 500 seconds is the one that one of the problem we tested in the paper we published lately with the most complexity. A lot of the problems takes like 100 seconds or less. The solution will come out extremely accurate. How accurate? This is the example you can see. Okay, this is a comparison of the solution we constructed, we call it analytical solution because the expression, right? And B is Monte Carlo simulation with 10 to the 9 sample points, a lot of points. But again, this is a 4-dimensional space. And you project that onto a 2-dimensional domain, and you see a very typical Vanderbilt behavior. So the accuracy is extremely high with, remember, 4-dimensional space, 500 seconds. less than 10 minutes. So it's quite amazing. This is a projection on another subspace. Okay, so it's just quite accurate, amazingly accurate. So let me to just conclude my talk. So we had a recent study on data-driven global analysis, and we now apply this method to study some very interesting examples, such as the ocean current flow pattern by using the satellite data. And we can predict the dynamic behavior of the current flow in some ocean. Okay, we have a recent paper just coming out. And then with the solution to the FPK methods equations, we actually proposed the method that can substantially speed up the solution process of very complicated stochastic nonlinear dynamic systems. So we found that the concepts and the methods from the data science can really change our way of thinking and generate really significant impact on the traditional research in dynamic systems. Thank you so much for your attention. Bye-bye.